Today I want to start what is probably going to end up being a series of lectures and probably will eventually be online lectures, but I haven't had a chance to record them yet. I want to start this series of lectures about NMR, but what I want to do is I want to talk about sort of the more advanced aspects of NMR and with an eye toward some of the theoretical things and how they then impact what we see or change some of those basic things that we talked about when we try to look at NMR and solve problems. Okay. So what I'm going to start with here is the basic theory of NMR. Like, how does NMR work? And I've tried to, I tried to boil this down to as little as possible, and it still ended up being 5 pages. So, but it is kind of important that you begin to visualize sort of how this instrument is working, because there are some things that we're going to see in terms of chemical shifts, in terms of equivalence and stuff like that, that are going to be affected by literally the physical, actual way that the instrument works. Okay. And so that I can't really explain them unless we have the physical way that it works. Okay. So we're going to start with, I don't know what this thing is. I thought it was like a little pointer, but we're going to start with the idea of nuclear spin. So when they were doing quantum mechanics and they were sort of starting to calculate all of these quantum mechanics properties and stuff like that, they ended up calculating a property for nuclei. So the actual center of the atoms. And the property basically was that if a nucleus had an odd number of protons, or it had an odd number of neutrons, or both, so one of those 3 cases, then it turned out they calculated it would have the nucleus itself would produce a magnetic field. And I'm going to show you a picture of that down farther on the notes. But basically, there's this magnetic field, okay, and they called this magnetic field the nuclear spin, or we just often just call it the spin of the nucleus, okay? And this is actually similar to the spin of electrons, which I don't know if you were ever introduced exactly that term, but you know how when we do electron filling, we draw these arrows, one up and one down? And that it's pointing up or pointing down, that's the spin of the electron. So it was just, they calculated that property for electrons, and then they found out that certain nuclei would also have that property, if that makes sense. And in fact, I've put a table here, and this is not something that you would be asked to memorize, and I wouldn't really ask you a test question about this necessarily, but I just want to show you kind of how this plays out for the purposes of organic chemistry by looking at some atoms that we might use in organic chemistry. And there's a couple more, but I left them off. It's not really a big deal. They're minor things. But if we look, for example, we can see that the hydrogen nucleus, it has 1 proton and 1 total particle in the thing. That's what the 1,1 means, right? The 1 on top is the total number of particles in the nucleus, and then the 1 on the bottom is the number of those that are protons. And so, by taking the difference, that would be the number of neutrons. And so if we look, hydrogen 1 or 1 hydrogen, whatever, has an odd number of protons. It has no neutrons, okay? but because it has an odd number of protons, it has a spin. And then, in fact, the spins, it has two spin states. So we're going to look at that. It's either spin pointing up or spin pointing down. Some of the other nuclei have more than one spin state, more than two spin states. So they have like pointing up, pointing to the side, pointing down, or pointing up, pointing partly this way, and whatever. You don't need to worry about that right now. Turns out, fortunately, in a way for us, all of the nuclei that we're really interested in have only two spin states. So they work very much like electron spins. The other thing I want to point out is that basically there are isotopes of these elements, of these nuclei, right? And isotopes have the same number of protons, but then they have a different number of neutrons. And so, for example, there's a hydrogen isotope which has one proton and one neutron. So it's hydrogen 2, basically. And in fact, we usually call that deuterium, and often we use the letter D to represent that, even though it's still a hydrogen. And the important thing to know about these isotopes is that they're not present all in equal amounts. There's a natural abundance of them that we usually express as sort of a percentage, like of all of the nuclei, what percentage would be this isotope. And so when we look, 1H, which is just our regular hydrogen, is present in 99.98% abundance. In other words, it's the other ones are, less than 2 in 10,000, okay? Deuterium is present in only 0.156% abundance, okay? And that's important because we're going to see with carbon later on this semester that the carbon we want to use is present in a very low abundance. And so we have to have a very sensitive instrument because most of the carbon won't respond to our instrument. It also means that some of the interactive things that occur between nuclei that have spin are rare for carbon, okay? So again, looking down, carbon-12, which is our most common isotope, has an even number of protons and an even number of neutrons. So it is not active in the NMR. And that actually turns out to be a good thing because that means we don't have splitting between those carbons and the hydrogens, okay? But when we want to do carbon NMR, it turns out to be a bad thing because carbon-13, which is the NMR active carbon isotope, because it has an odd number of neutrons, is present only about 1%. So we need an instrument that's like 100 times more sensitive to be able to see the carbon when we compare it to the hydrogen. Okay, then you'll see, again, oxygen does have an NMR active isotope, but it's very small abundance, and it has a lot of spin states. And quite frankly, I've never actually personally seen an oxygen NMR, although I'm sure they must exist. I have seen a fluorine NMR, and fluorine turns out to behave pretty much like a hydrogen. It's 100% abundance, and it has two spin states. And so you just have to change the frequency, and it can be useful. Like if we put fluorines in, we can get information. But okay. So this is a picture of what the magnetic field of a nucleus looks like. Okay. So a magnetic field actually exists as a loop. Okay. It starts from some originating point, so we say kind of in the center of the nucleus, and then it kind of comes out, it goes around the outside, and it comes back in and meets up at the beginning. Okay, and this is important because magnetism has a direction. So I don't know if you've ever played with magnets, but if we play with simple, just, iron magnets, they have a north end and a south end, which just basically represents that there's a direction to this thing, to this magnetic field. And, north repels north, but north attracts south and so forth. Okay. And so what we see here is that this magnetic field, the magnetic field inside the center of the nucleus and the magnetic field on the outer side of the nucleus are going in opposite directions. So when we look at a magnetic field loop from now on, the inside of the loop will go in one direction, and then the outside of the loop will go in a different direction. And we're going to see that's important when we look at the magnetic field that occurs around pi orbitals, pi bonds. Okay, so, well then how are we going to deal with this? Because what we have is we have something that has both a size, like a magnitude, and a direction, but really we have something that has two directions, or really infinite directions, because it goes all the way around, right? What we do is we, for the purpose of the nuclear spin, we use the direction on the inside of the nucleus to represent the direction of that magnetic field. Okay, so we're using this portion here right there, the direction inside the nucleus, and that equals that arrow. And so usually what we do then is we abbreviate this. Instead of writing all these loops, we just put an arrow inside the circle of the nucleus to show that that's the direction inside the nucleus of its magnetic field. So hopefully that makes sense. It's just a little bit of like, how do we use symbols to represent this stuff? Okay.